Hello, everyone. Welcome to our workshop today. I will be hosting a workshop about building a smart Passkey wallet with account abstraction. So my name is Farhad, and I am a software engineer at Clave. So we're building a account abstraction wallet on ZK Sync with Passkeys. We're trying to simplify the user experience of the crypto usage in the wallet level. So I will be firstly giving the technical background about Passkeys, account abstraction, paymasters, some other technical details about the account abstraction and the Passkeys. So then we will be going to live coding. So if you want to join to the coding part, you're invited. So firstly, I will be talking about what is Passkeys, account abstraction, smart wallet, and explain some technical terms about it. So probably you have used Passkeys before. If you used Passkeys before, you can raise your hands. Yeah, there are lots of people. Passkeys are basically tools for doing two-factor authentication in the web in the current state. So big companies started utilizing Passkeys with their authentication flows like Google, Amazon, and other Web2 companies. So why don't we use this? Why don't we use it on the blockchain industry? So I will be explaining those, and then we'll be talking about the account abstraction. So account abstraction is simply a way to have your wallets in a programmable way with different verification methods, like any custom logic that you can apply on the smart contract level to verify your users. Account abstraction also introduces the batch transactions where you sign only once for multiple transactions. So instead of doing approval and transfers or some other multiple operations with different signings, you just sign once and send those transactions at the same time. Account abstraction also introduces paymasters where you can sponsor for your gas, sponsor the gas of the users, or users can pay with any ERC20 token for their gas. So we will be also utilizing Passkeys today in our live coding session. We will be building a gasless paymaster to sponsor the gas of our users. And also we will be building with the native account abstraction. It's pretty similar to the normal account abstraction, but introduces it in the protocol level of the rollups, in the current rollups. And we will be building on a rollup called ZK Sync because we have a short amount of time. We have only 2 hours, and we will be building a complete wallet from scratch, from zero to the production level, kind of a production level wallet. Also, we discussed about Passkeys and why it's not used in the current blockchain world. It was the reason behind that is that the Ethereum, also Bitcoin, uses an elliptic curve called seg P256K1. So it's kind of an elliptic curve which produces signatures, and you can validate those signatures on the smart contract level by simply calling some libraries, ECDSA libraries. But the signatures given by the Passkeys are different. So in the current modern devices like your iPhones, your Android phones, and also Mac devices produce a signature that is odd to Ethereum world. So these signatures are given in the different elliptic curve called P256, or also seg P256R1. Maybe you've heard of it. So there's a no optimized way in Ethereum to verify those signatures, and precompiled contracts are introduced using RIP 7212 to verify those signatures in an optimized way as we do it for normal Ethereum and Bitcoin signatures. So today's goal is building an authentication with Passkeys in the wallet level. So we will implement a simple transfer functionality with your biometrics. We will introduce gasless transactions with paymasters, and we will be using multi-call to get multiple token balances for your account. So normally in the normal wallets, you just have to send multiple RPC calls to the network to get the balance of your account. But with multi-calls, you can just simply collect the user's balances with just one RPC call, and we will be also building this. And we will be also seeing the batch transactions, as I previously discussed about, which is like combination of transactions with the same signature. At the same time, you're just sending multiple transactions instead of signing those transactions multiple times. So this is important for wallet user experience. If you have used AOAs before, you probably know that for example, in the swapping, if you want to swap from USDC to ETH, for example, you have to first approve your USDC and then swap. And even if the DApp is not implementing it correctly, you will have approvals left behind, maybe an infinite approval, which might be risky for the future. So with the batch transactions, you can handle everything in a way that it's secure, it's easier to use, and just sign once, send once, and done. So we will be firstly setting our repository in the workshop. So I will be going back to my computer. So I've prepared some starter repository for today. It's simply a repository that helps you to start your coding. It's special for today, so you can, if you want to join the workshop and do the live coding, you can go to my GitHub account. And in this QR, there's a repository for getting started. And let's see a bit what is inside this repository. So it shows you the ways how you can set up your development environment with the packages. It gives you the SDK for working with the smart accounts, also with Passkeys, and you will be initializing it. It talks about the components of the SDK and also creating a passkey for your account, using the existing passkey, sending transactions, and sending batch transactions are also described in the README. So we will start by simply cloning this repository, and then I will be going to the live coding and also explaining some passkeys after like showing how you can clone this repository and set up your development environment. So I will simply go to my terminal and go to my working directory and create a test folder so that I can just simply write git clone and the URL of the repository. So it will be cloning some files, and it's in the test. Oh, sorry, I cloned in the wrong place. So I will be cloning again. Also on the README file, it shows you the way how you can use the submodules, because we will be using the open source contracts developed by us, so that there's no need to worry about the smart contract side, so that you can easily start to your development on the client side. So I will be also showing those contracts, and we'll be also building a passkey validator contract from the existing ones, and I will be explaining the things that you should do on the passkey validation on the smart contract level. So to update the submodules, which is located in the repository, you just simply need to copy and paste this inside the repository. So it's cloning the files from the submodule itself. So yeah, it's there. And you need to also use some private keys to deploy your smart contracts and also deploy your smart accounts. So in our contract stack, it's defined that you need to use the same private key for deploying contracts and also deploying the smart accounts produced with the produced from the factory contract that we are going to deploy. So to not expose my private key, I will be just using the pre-cloned version of the repository. So everything is here. And I will be starting to the contract deployment, but also let's go back to our slides and discuss more about the smart contract deployment. So today we'll be deploying these contracts with just one command. So I will explain their purposes. So we have some 6 or 7 contracts. Yeah. The batch caller contract will be used for sending batch transactions. The implementation contract will be used for the main implementation of our wallet. The registry contract will be used for storing your addresses in the smart contract to identify that this account belongs to your contract stack. The gasless paymaster will be used for implementing gasless transactions. The proxy is not important for today, it's for future. You can use upgradable contracts to, like, you can upgrade your contracts in the future to change them if you need. So the Passkey validator will be used to validate the Passkey signatures. That we will be also showing how you can build a Passkey validator contract. And also the account factory is basically the contract that deploys, that produces your accounts one by one. And also, since we're building the Passkey validator contract, we need to understand the components of the Passkeys authentication. So the Passkey, if you try to sign with the Passkey, try to sign a message with the Passkey, it simply produces an authenticator data that contains the information of your RPID, hash, and other related stuff to your authentication, whether you gave the biometrics or not, whether user set up some flags in the authenticator. The client data mostly contains the challenge that you want to sign. Challenge is basically the message that you want to sign. It's called challenge in the WebAuthn standard. Also the signature that will be provided, which is a P256 signature, as I previously mentioned. So we will be showing the how you can verify and create a Passkey message and verify it on the smart contract level. So it's simply the hash of the authenticator data plus like the concatenation of the authenticator data and the client data hash. So let's go back to the main part where we'll be building the wallet from scratch. So, oops. Yeah, since we cloned our repository, we can continue by setting up our deployments. So I will open a terminal in my repository, in my local repository, so that I can go to the contracts repo. So in this contracts repo, you can just simply, after putting your environment variable, you can simply go to, like we will check whether we have enough balance in our account in this private key that private key belongs to. So I will be using a ZK Sync Sepolia testnet, which you can find the details from the chain list or any other source. And since I have enough gas to pay, enough Ether to pay for the deployment, I will be just running a command to deploy them. But firstly, we'll need to go to the smart contracts repository and build our validator contract, which is a Passkey validator. So in this contract stack, you see an existing Passkey validator, but we will not be using this today. Today we'll be building our own, because this contract contains some constants to optimize your gas. But for today, we don't need them, because you need to debug your authenticator data and client data that I described before to make it like optimized. So I will be just copying this file and also creating a new validator over here, calling this Passkey validator Devcon, and pasting this to here. So in the validate signature, you can see that there are two types of signatures that we can have. So the first signature that's included in the first if block is simply the optimized way to validate this signature. But we'll be using, as I said, the non-optimized way to validate this signature. So I will be just removing this part and just keeping this validate fat signature function over here. So let's check the components of the fat signature that we called. So it contains the authenticator data that comes from the Passkey authentication, the client data suffix, which will be concatenated with the given challenge, and the client data prefix, which is always the same. So you can simply hard code it. And also, the RS formatted signature will be provided from the client side so that it gets validated. We have some malleability checks over here, and also the flags are controlled so that it contains the user presence and the user verification flags of the authenticator data. If you go back to slides, over here you can also go to the Mozilla docs about the authenticator data and about the client data over here, so that you can see that the client data JSON or client data includes your challenge itself. The challenge will be the transaction data simply. So the concept is, instead of signing random messages in the Web2 world, we will be signing the actual transaction data as a challenge, so that we can understand what kind of transaction the user sends and what kind of transactions to validate. So everything in the Passkey world is base 64 URL encoded. So you need to make sure that your challenge and other parameters are also in the base 64 URL format. So we concatenate the challenge data prefix, our challenge base 64, and the client data suffix, and then create a message by simply like hashing them and combining them together, and then call the P256 verifier contract, which is defined with the in the zk-sync core. So when we go back to the explorer of the zk-sync, when we paste this address, it's simply 0x100. You can see that the contract exists here. So it's a P256 verifier contract that is a precompiled contract, so that it verifies your passkey signature in an optimized way. Let's go back to code and remove some stuff over here, because these are simply for optimization, as I told. The authenticator data hard-coded version is also not needed, and we can simply remove this function too, because this is the optimized signature verification. We're not using this also. And I think everything is right except the name, Passkey Validator Devcon. We will be calling this like this. And it looks fine. And we can simply continue by running the compile command to generate our contracts, to compile our contracts and get their artifacts. And we will be using the deploy MVP script, which simply gets all the artifacts and deploy the contracts one by one, as you can see. And it gives the required constructor parameters to each contract so that they work well together. And then it simply logs those contract addresses so that we can use them on client level. And we will be using the Passkey Validator Devcon as I named it like this. Let's check the name again to not fail. Yep, it looks fine. So I will be calling the deploy MVP command. And the contracts are getting deployed there. So it will take like 2 to 3 minutes. Since here, if you have any questions, you can feel free to ask. Or I will continue to the client level and explain some components of the client. It's also in the same repository. Yep. Do you have a microphone, by the way? Or, yeah, you can ask. Yes. They were at the validators folder. Mm-hmm. And I just copied and pasted the validator, Passkey validator.sol, and created a clone of it, and simply just copied, pasted this file, and removed some of them.
Okay, so what exactly do we have to remove?
So you need to just, from this contract, you just need to remove this part, and just keep the validate fat signature, and also some constant values over here, like this line, this line, this line, and yeah, that's it. Okay. But you can also use the same contract for this workshop, because they both gonna work, because the client side just uses the second part. Mm-hmm. So it's just enough to use the existing contracts.
Okay, thank you.
Yeah, sure. Here it is. So yeah, I will be moving to the client level if the contracts are deployed. It's still getting deployed, but let's go to the GitHub and see the more documentation about the existing client. So we will be defining our Smart Wallet SDK, which is I called in my NPM package. So I created an NPM package for this workshop so that it gets easy for you to get started. You will be just copying and pasting the smart contracts that produced from the previous step after our deployment. And we just need to initialize the Smart Wallet SDK instance and give the chain ID, which is 300, which is the chain ID of the Sepolia ZK Sync. And the contracts, also optional, the API URL will be used for deploying your contracts. So as I previously mentioned, you need to deploy your smart accounts with an AOA, and you need to put the private key of your deployer, of your smart contract deployer to the client level somehow in a secure way, so that you're also able to deploy the smart accounts in a correct way. So the SDK includes the core, which is helpful for preparing the transaction call data. The deployer will be used for deploying your smart accounts. The multi-call will be used for having multi-read operations, and the WebAuthn instance will be used for utils for the passkeys. It's simply an extension over WebAuthn to simplify the passkey operations. So I will be showing those functions, like we will be running the client application on our local and code each part one by one. So here are the smart contract addresses, as you can see. I will just copy and paste it to my client side. So I can go to my client, and I will be initializing my SDK on the source, and I will call it sdk.ts. So we're working with mostly TypeScript because there are lots of libraries to work with, and it's quite going well with the web development. So what we need to do is, let's put them here, but we need to also get the codes for initialization. So yeah, these are the codes for initializing your SDK. We just import the smart wallet SDK and then set the contract addresses. And we don't need API URL for this workshop because we'll be using the local host one. So you don't have to override it. But if you want to deploy it somewhere in the web to share with your friends, you will need to update this API URL value with your domain. So the SDK instance is ready. We can close the terminal for now. And we can start our development environment, as also described in this README. So, so you don't have to do anything after this. You just need to run the npm run dev to run the development run the development environment. So I'll go to the client and run the dev environment. So I need to just go back to my previously cloned version because like my private key exists there. So it's in my smart wallets directory. I can go to clients and just npm run dev. So as you can see, it started the localhost 3000 for the development. When we go to localhost 3000, it welcomes us with a simple UI that says that you either need to create a smart wallet or log into an existing one. So we will be implementing all these steps, like creating and the logging part, so that you are able to like create a new account and also log into an existing account. So to do this, let's also check the architecture of our client application. It simply contains some components like UI components, some constants which defines the token addresses, their pictures and stuff, some hooks to get balances, and it uses some global state management tools for storing the credentials in your local, and also some utils over here. And the main thing happens on the views. So in the when we go to the layout, you can see that you can see that on the there are two views, like home view and the auth view. In this part, we will be seeing the so when we run our development environment, we only see the auth view where the authentication happens. Like there are two steps: the deployment and the login. So we will be firstly implementing the deployment. So let's go back to our README file and just copy and paste this registering part and put it to the deployment. We need to import the SDK that we created, the SDK instance. And finally, it gives us the status, and if it's 1, it means that your deployment is successful and you can continue and do some other operations like setting a global state and more. So I will just throw an error if the deployment is failed, and then set up some global state over here. So there's a hook in the repository called set credential. So this set credential is simply holding the credential ID of your passkey. It's the unique identifier for each passkey and the public address that is produced when you deploy the account. So we need to create our credential first of all. So the credential is simply the passkey ID and the public address, and we will set the global state, as you can see, and then we will be initializing our core instance with the given credential, and we will also set the set this credential to the local storage, because when we refresh the page, we need to somehow get the latest account that we logged in or registered. So that I also created a storage instance, storage util, so that it's helpful for like setting JSON formatted values to your local storage. So it's also defined with the storage keys.credential. It's simply a string value that defines for which key this value should be set. And also you will need to pass the credential over here and also use the set JSON item, because this credential is an object value. So it works so that it works. So it only accepts string values on the other case. So we will just use the set JSON item function. So let's go back and see whether it's going to work. So when I try to press the create smart wallet button, it will probably fail because I missed some part, but I will explain soon. So it's loading because it cannot deploy, because we need to deploy our smart account in an API level, which is defined in the route TS inside the app. So Next.js applications allow you defining APIs on the client level so that you can securely put your environment variables in inside your app and use them on the server side. It creates a node environment for your client application. So here we need to put our factory contract address that we produced before, which is also, we put also to the SDK instance creation part. And I will just paste this account factory to here. And as you can see, it's thrown an error because it couldn't find the address of our account factory. So I'll go back and refresh and try the deployment again. I will give my biometrics, and it should work. Yeah. So we deployed our first account. We can go to the block explorer and see what's here. So when you see a contract over here, it means that you have deployed there's a contract associated with this address. So this is not a dummy address. So there's a contract. We failed to verify this contract, but anyways, it's simply the main implementation. So what we can do now is simply go back to our application and see that there's a disconnect button over here. It means that log out from your smart account, and we will implement the login part to use the same passkey. So when you go to the passwords of your device and go to the local host, you can see the passkeys over here. Like this is the one that I created in the latest time, like 1 minute ago. So the passkeys are bounded to your domain. So if you create a passkey on your local host, you can only use it on your local host. So you have to be careful about this if you build an application. So passkeys are, as I said, bounded to your domain. and only used in the domain that they are created. So we will implement the login part to use the existing passkey that we created like 2 minutes ago. It's also defined in the README, so you can just simply copy and paste this inside the auth view. Auth view, if you forgot, it's simply this page. It's simply this page, and in the login account function, we will be implementing the login to the existing passkey. I'll just remove the comments. I will again build the credential object, which is the passkey ID and the public address, which is located inside the passkey response.user handle. So user handle is the passkey ID that we provided in the registration part. And when you try to let's read a bit this code. So this library that I built is actually using a passwordless ID /WebAuthn open source package, which is also doing some passkey operations. And in the authentication part, it simply passes the credential ID and a random challenge to sign in the login, and some auth options like some other configuration. And during the creation, during the registration, we simply get a random username, which is the current date, and also the random challenge to create our passkey. So in the login account, we should have to do the same thing, like set the global state, set the local storage, and also connect our SDK to this credential. So when I go back and refresh, and press the login to existing wallet, as you can see, the passkeys are shown here. This is the latest one that I created, and I pressed this to choose it and give my credential, give my biometrics, and I logged into my smart wallet. So it says loading because it cannot fetch the balances. So we will implement the setting balances. We will also implement the like restoring our state, because when I refresh the page, as you can see, it's gone. We have to press login again and sign in. But we have an easier way. So when we set the local storage, as you can see in the local host, there's a credential value which stores our credential ID, which is a passkey ID, and the public address that I created in the last registration. And to use this, we have to go back to layout. There's a component called state setter, and it simply gets the credential from the local storage by simply calling get JSON item from the storage instance. And you need to import these values from the store and the utils to get the types, since we are using the TypeScript. And also the set credential global state setter again comes here. And again, we need to connect the sdk.core.connect with this credential. So you simply build an object which has a passkey ID and a public address, set it to your store, set it to your global storage, set it to your local storage to restore it, and use these values for sending transactions. So when I refresh the page, as you can see, it's already restored, and it's the same address that I previously deployed. So there are two views, two main views over here, which is a receive and send. We will implement a transfer functionality, and also the receive is already there, so this QR code contains your address so that we can fund. But before funding, let's solve the balance fetch issue, which is located in the use balances query hook. There are some commented places, so we will implement it from scratch. Let's just comment it. Let's just remove the comments. And as we previously saw, there's a multi-call instance inside the SDK, and it already contains the get token balances function, which is simply sending some. It simply generates some RPC calls and combining them together. Like it calls balance of function for the ERC20 interface, and also for ETH, it's not the same as ERC20, so you need to call some other values. So you need to make some different RPC calls. So it contains, you can read the codes from here, but I will not go deeper. Just call the get token balances, and also pass the addresses of the tokens that you want to get the address of. So import the balances, which is simply the mapping of mapping of the addresses to the balance of that token. And we will set the global state of the balances. And also there's another global state that is called isBalanceSet, which is used for controlling whether we could successfully fetch the balances or not. So it should be ready. So there's also, when we go back to the balances query, as you can see, it refreshes this query every 10 seconds, so it will get your balance in every 10 seconds, and you will see the updated balance. So when we go to home, as you can see, we have fetched the balance of ETH, USDC, and the Tether. So we will be using with Ether today because I don't have enough USDC on testnet. I will be showing the operations with the Ether, but the ERC20 tokens are quite the same with the Ether if you want to generate transaction. But I will be showing how you can create transaction call data with the util that I built. So to do this, we have to fund firstly our account. We can just go to receive, copy our address, go to my MetaMask, and I will send some money to my wallet, and let's see whether I can see it in my client implementation. So I will send some ETH to it, let's make it 0.005 ETH. And I'll go back to home and see whether this refreshes. Yeah, as you can see, I have now 0.005 ETH in my balance. So I can use this ETH, I can transfer to someone else. I can use batch transactions to send it to multiple users at the same time. And when I go to send, as you can see, this place is also not implemented. When I go to send view, this is the place of this page. This is the codes of this page. And we will implement the transfer functionality. But first of all, let's comment this out because it also uses some utils from the library that I built, and also gets the balances from the global state, which you can access by simply calling use balances hook. So it also formats this big number, which is defined in ethers. It's simply formatted to a human readable way, so you don't have that you don't have 18 decimal values on the UI. It somehow prettifies it to a 6-digit. Let's go back and see that we can see our available tokens in our wallet. And also in send view, let's see what states we have. We have a value that simply holds this place. You can just enter some digits, the amount that you want to send, the ETH amount, and the address of the recipient. So of course you can improve this implementation to send to usernames, for example, that we also do on our own Clave wallet, so that you can send to your friend's username instead of addresses. Or you can also improve this to accept the ENS of your friends, so that you don't have trouble by just copying and pasting the 20-byte address every time. So I will send the money to myself right now. I will not implement the that resolver, like ENS resolvers and stuff, I will just copy and paste the receiver address and send some ETH to it. Let's send 0.001 ETH. And to send an Ether, we need to implement the transfer logic, of course. When I go to my README file, as you can see here, we have an implementation for sending the exact amount of Ether. So I will just copy and paste this. By importing the SDK, I can access the core. And for the to value, I will set the receiver, and the value I will set as the amount that I entered, which is stored in the value state. So you need to also parse the Ether value because the Ether has a decimals of 18, and the parse Ether is basically adds, like multiplies this value to the 10 to the 18, so that the blockchain understands how much amount you want to send. And also you will be calling the sign and send function from the SDK. So we went to the node modules and see what's inside. So this function also appends a paymaster to your transaction so that you don't have to worry about paying the gas. So you will simply pay for your user's gas so that people just simply can send transactions without worrying about how much Ether they have for the gas. So it gets the transaction by calling the sign function. It simply does some interesting stuff from the things that I implemented. You can also read those codes from the repository. It's open source. But since we don't have to worry about the difficult parts over here, we just have to create the transaction which simply like sets the transaction object for your blockchain, sets some required parameters like gas price, gas limits, chain ID, and other parameters. And we'll be signing with the passkey and then sending this transaction to the network to get validated. I'll go back to the client application and press send. This transaction will probably fail because we, again, didn't do something that we should have done. So as you can see, it errors with the failed to validate a transaction. The reason is paymaster validation error. So when we go back to our addresses that we deployed on the client, we have a gasless paymaster over here. So let's paste this to the Explorer and see what's inside. So I'm in the mainnet. I should go to the Sepolia. Okay, as you can see, there's a contract called gasless paymaster, and it has no balance inside. But since we are paying for the fees, someone has to pay for the fees, and this paymaster will hold some Ether inside to sponsor your transactions. So I will send some money to this paymaster. So you need to eventually check your paymaster address if you want to go in production, so that you don't get out of funds, so that users don't have to pay for the gas. I'll just paste this address to my MetaMask and send. Let's send $100. It's too much for now, but anyways, it's the testnet ETH. So when I refresh, as you can see, my money is here so that I can start sponsoring the transactions of the users. Let's go back to the client and refresh again. So I have 0.005 ETH, and I will send again the same transaction, the exact same transaction that I previously did. Copy paste my address to the receiver and send 0.001 ETH to this address. I'm again giving my biometric authentication. So it appends the signature and sends the transaction. So the balance will be updated in 10 seconds. But As you can see, it went down to 0.004. We can go back to the address on the Explorer and see the transaction history. So what happened here? So in the transfers part, as you can see, I just now sent 0.001 ETH to this address. Let's go to the transaction and see inside. So here, the Zcasing Explorer shows that this fee is paid by Paymaster, which has an address of this, and it's paid for the 3 cents transaction fee. Let's close this page. So we can improve this part by simply calling another function over here to update our state much faster. Like I'm using a React query for this repository, so it's a helpful tool for sending an API request to somewhere or sending like RPC calls, etc. I will be just calling a refresh queries function from the React query and passing the key of the balance fetcher query, which is defined here. As you can see, it contains the queries. It contains the balances value, which is a string value, and the public address of the user, so that we set the balance for each user, each registered user. So to refresh the query, I need to call this refresh query function and also pass the query key. So let's try it and see whether it works. I will again paste this address and start and send. Let's send a bit low amount so we can see full balance. Okay, it went down. As you can see, my balance went down. So for the next part, we will be sending a batch transactions. So as I previously discussed, batch transactions are used for combining multiple transactions together so that you just sign the transaction once and then send to the network. So we will be using some utils again from the SDK that I built, but we will be sending an ETH amount to different addresses. So let's go back to send view and expand this part as like add another state as receiver 2, and also the value 2 to send also different amount to different addresses. The selected token will be the same, and I will be putting another input over here so that we can also set the state for the second receiver. So this is the receiver 1 and this is the receiver 2. So this sets the state for the receiver 2 and also contains the value of the receiver 2. And this is for the first receiver. So let's go back to the send. And as you can see, we can see now 2 inputs. We have to set. We can just remove this value to send the same amount to not lose time. And I think we are ready, but we need to implement the batch transaction function. So I will comment out this part and simply start again by using the batch transaction util from the core instance. So as you can see, there's a function called get batch transaction, and it simply accepts array of transactions which has a to address, a value, and the call data. So since we are transferring ETH, we will be just setting the value and the two fields. So when I go back to my get batch transaction function implementation, I will be setting the 2 as receiver and my second 2 value as the receiver 2. I will also putting the value as I did before, like I have to multiply it by 10 to the power of 18 since Ether has this decimal. I will be setting the same amount for this for the second receiver. Again, I will need to call the sign and send method from the transaction instance that I created, and also refetch the queries. So let's go back and see how much balance we have. So we have 0.0039 ETH inside, and I will be setting 2 different addresses to transfer money to different addresses with the same transaction. So I'm setting my address as the second receiver, and also my my main wallet as a first receiver. And let's set the amount of 0.001 and start sending transaction by, again, we need to give the biometric authentication so that it goes to the smart account Passkey validator and gets verified. As you can see, my balance is down to 0.0019. I sent 1 ETH to each user. Let's go back to the Block Explorer and see the transactions. So in the transfers, it seems like multiple transfers, but I actually sent it with this method to the blockchain so that it transferred twice, but actually I sent 1 transaction. So let's go to the transaction and see what happened again. So as you can see, our wallet transferred 001 ETH to this address and this address with the same transaction. And also we sponsored for the gas. So let's go back and see what else we can do. I think the implementation is done for our wallet. So what we have in the end? So we have a smart wallet that we can log in, and like in the beginning we all of course like deployed our smart contract, and now we can just simply log into it with our biometrics, which has like we have a multiple RPC calls in the home page so that we fetch the balances for different tokens. We have a send functionality which we can send multiple, which we can send Ether to multiple users at the same time with the same transaction, so that like you don't worry about the gas fees and other stuff. And we sponsor the transactions with the gasless paymaster. And we also have a place to receive your funds from different wallets so that you deposit, you top up your balance. And you can, of course, like disconnect and create a new wallet, continue to your path with the new wallets, and do additional things. So let's talk about a bit. I can accept some questions if you have any. Yep. Thanks.
About the domain restriction of Passkeys, and it's a wallet running on your app. Obviously, if it's a wallet that you want to integrate with that,
Yep.
what's like the best current best practices for that, like an iframe, and are there any restrictions of using Passkeys in iframes?
If you're building a mobile wallet, there's no restriction for the web views on iOS side. But Android doesn't allow you to use your passkeys on the web view. Currently, I think there are some passkey wallets that are built in the browser level, and they're using they're using a pop-up to navigate to users to their domains in another window, and there they sign for the transaction in that domain, so that they can use that same passkey for different. Yes, it works for the iframe on the browser level. Yeah. Yeah.
Can you associate multiple passkey? Oh, yeah. Dang it. Can you associate multiple passkeys to a single account abstraction wallet?
So yeah, the contracts that I showed is a modular account that can have multiple public keys inside. So you can assign like as many as possible, as many public keys as possible to the smart account. So how it works in this contract that I showed, it simply tries to validate over all public keys. So at the end, if it finds a correct public key, it validates the transaction. Otherwise, it fails. So this is possible because of the like RIP 7212, because normally like validating this transaction is taking too much gas, but with the precompiled contract, you can just like validate through the all public keys, and it takes like not too much gas. And in the current rollup state, it's just like cents, some cents.
That's just on ZK Sync.
Currently, the precompiled contract is deployed to ZK Sync and Kakarot, I guess.
Okay.
And some other rollups are also integrating it, and they will be live probably in the short amount of time. But since it's live on ZK Sync, I showed the demo version of the wallet on ZK Sync.
Got it. Thank you.
Yeah, please.
Can you, in a deterministic way, determine where the smart which is the smart contract address before deploying it really?
So yeah, during the deployment, you provide a salt to your account. So like you generate a random value for each wallet, so that you don't have like you don't run into the trouble that you try to deploy the same address. So in ZK Sync, there's a function called create2 in the system contract. So it computes the address for your salt value. So I can show from the code actually. So during the deployment part on the client side, we simply call the function from the deploy account, from the factory contract, which is called deploy account. We pass the salt value to the deploy account function, where it calculates the public address, and it's a deterministic way actually. With the same salt, you produce the same address. But the problem is that it's different for the other chains. For the ZK Sync, the create2 produces a different value for different public address than, for example, from base. So that this is the current technical problem on going cross-chain with ZK Sync and other chains. So you cannot produce the same address for ZK Sync and other chains. Yep.
How expensive is verifying the signal group? Because as you say, the elliptic curve function are different on the mobile phone and on the smart contract. So I guess that verification on the smart contract is insanely expensive.
Yes, exactly. So when we can go to the beginning. So normally the transaction, we will go back to here. So yeah, normally the Ethereum and the Bitcoin also uses an elliptic curve called SEC P256K1, but the Passkeys and Secure Enclave also uses a elliptic curve called P256 or SEC P256R1, which is different than Ethereum, as you mentioned. So it's really costly to verify those transactions. But there's a roll-up improvement proposal called 7212, which was an EIP before, which is developed from our team actually, some folks from our team. Let's go to the definition of it and see what it recommends. So this proposal creates a precompiled contract that performs a signature verification in the SEC P256 R1 curve, so that the verification cost will be exactly equal to the verification of the SEC P256 K1 curve. So in our case, we don't run into the trouble. There are some other like optimized smart contract implementations that we used previously, but they are like almost taking 50 cents for each transaction, which is quite high. But like after the blobs, it's like a bit less. But again, using a precompiled contract is always much more optimized. Yeah, please.
I'm next. Sorry. Here on the right.
Oh, okay.
Sorry. So my question is, we didn't get into that part probably, but you said that paymaster is paying fee for transactions, right? So could we get into that part, like you're trying to send the transaction for address A to address B, but some other address is paying for fees, right? How is that done in your example?
So you mean a wallet B pays for the
Yeah,
address wallet A?
No. You have. I'm sending a transaction from address A to address B, but some other address C, for example, is paying for fee, which is your case, right? Where paymaster is paying fees, right? Am I right? Did I get it correctly?
Like currently, the paymaster is a separate contract that contains a balance inside, which has a custom code inside. So it checks, it calculates how much gas the wallet A should pay, and it checks whether I have a balance, the paymaster has a balance of that value, and pays for the gas. But the wallet C, I cannot imagine a way because...
Not wallet C, address C. You're sending a transaction from address A to address B, right?
Yeah.
But the thing that I didn't get probably or was not presented is that you were saying that address A won't be charged for a fee.
Yes,
Am I
exactly.
Right?
Yeah.
Yeah. So somebody else is paying that fee.
Yes.
And that's what I'm asking. How is that done?
Yeah, like the payer is actually the contract itself. So with the account abstraction, you can create a contract and put some money in the contract. So when you send money from your account to another account, that contract, you add that contract address and like prepare a paymaster data. It's called a paymaster contract. Put that paymaster data inside the transaction object. So it also like checks for the balance of the paymaster contract, and the paymaster pays the fees.
Yeah, and that part is clear. But if contract does that, if contract is paying for fees, and address A, that is sender, needs to tell to that contract what to do, and that's possible only through a transaction, and the fee for that transaction needs to be paid.
Yeah.
Who's paying it?
The paymaster contract.
And that?
Yes. Yeah.
That part is not...
Like I will show like the paymaster addition to the like the transaction in generation. So when you go to the, so this is the code that I built for the SDK. So it's simply when you try to send a transaction, it appends a paymaster to the transaction data. So this append paymaster is simply adding the gasless paymaster address and telling that this is a general purpose paymaster, which is a gasless paymaster in our case.
May I interrupt you
Yeah,
here?
sure.
So now we have a transaction like setting from, setting to, setting data, setting custom data, right?
Yeah.
But that transaction needs to go to a contract. That contract will know what to do next, right?
Yes.
And that costs something.
Yep.
It's going to a
So does that mean when I see that transaction on the Ether scan that I'm not the sender of it?
Like it's actually like this in the other chains, but ZK Sync supports a native account abstraction so that there's no bundler. You just send the custom type of transaction to the ZK Sync network using a provider instance of the Ethers, for example, and contract like the network itself understands who should pay the gas and who actually sent the transaction. So you actually correctly see the sender and the paymaster on the Explorer level. But in the other chains, it seems that someone else sent the transaction. It's actually shown in the internal transactions. Like there's a new tab in the Ether scan. Maybe you noticed that.
Yeah.
It shows in there, but in the ZK Sync, since there's a native account abstraction, it's shown in a correct way.
Okay, thank you.
Welcome. Yeah.
This is kind of an aside, but do you know the latest on the proposal that you just mentioned in terms of integrating that to an L1, like adding the precompiled to mainnet, let's say? Is that going to happen, or has that just kind of blocked?
Yeah, there are some like updates about this, like in the internal talks with the Ethereum team. There are some talks about like implementing this to the mainnet, but the proposal is suggested by the Ulash from, like, he's sitting on the left side of you. Maybe he can answer about this question, like whether it's gonna be happening on the mainnet or no.
Hey, current next hard fork picture is currently very overbooked with lots of proposals, so I don't see that's very realistic for the Pectra, but it's still on the CFI list. And if some of the core devs or client teams focus on implementing this proposal and advocating that much, we can have it on Ethereum, maybe in Pectra, maybe in Pectra B, which is separated into 2 forks, but at least now we have on each major rollups, including Optimism and Optimism Ecosystem rollups, ZK Sync, all ZK Sync Elastic chains, and in Arbitrum soon, I think we are having adoption, and it's still good. Do you need on L1, for example? Why do you need on L1?
I'm just curious.
Okay.
Yeah, any more question? Yes, please.
Hello. I'm curious to know like how this can be used in a real world. So what I understand, we use private key to deploy contracts. Then we have used client, the UI part, and we are sending the funds. So if we have private key, we can use that private key directly and send the funds. So how this can be used in a real world?
In real world, you mean,
Yeah.
right? So the private key on the, like in the client level, is actually for deploying the account for the first time. So it's not used in other cases. So in the first part, when you deploy an account, someone has to send a transaction, but there's no signer in the beginning. So we use that private key to initialize our contract. After that, we can just throw away that private key and do not use it. We will be using just the Passkeys private key, which is actually like it's embedded inside your device, so you cannot like reach it. You can just sign transaction with that without knowing what the private key is. So in the real world, you can have an account abstraction wallet. So you deploy this wallet with some private key. You just throw away that private key. You will not use it, and have a somehow like hardware level security in your phone. Some kind of a, like the most probably the secure way to send the transaction with the account abstraction right now. So we are currently building that kind of wallet. So there are some real world usages.
Yes, got it, clear. And I have second question. That is, we have run it on localhost, right? So I can run it on separate machine and the client, not a contract, and use the same addresses. And I also create a passkey there. So I can have 2 passkeys for single account if I have the addresses. The master address and all the addresses we get after deploying the contract. So I can deploy multiple instances of that and access the same account. Is that
Yes, exactly.
I'm understanding correctly?
Yeah, I got the question. Like in the first part, you can, of course, you can like move passkeys from one device to another if you want to say if you want to use the same passkey in different accounts, and it's automatically done on iOS, and it's automatically done with the Chrome, as far as I know. Like if you create a passkey on your first Android device and use the same Google account for those 2 devices, you will have the same passkey on the same devices. But on the second part, you asked about using 2 passkeys for the same account. Yes, this is also possible. You can have 2 public keys inside your smart contract to verify true, and you will just add one owner to your smart contract and then add another owner to your contract. You can add X amount of owners to your contract so that you will have multiple passkeys for the same address.
Okay, got it. Thank you.
Yeah, but you will be, like each passkey belongs to the one domain, so you cannot change the domain after that. So you need to be careful about the passkey creation, so where it's created, whether that domain is accessible, like some other concepts if you want to go to production. Yeah. So, yeah. There are some questions from this. I didn't know that there are some questions from the live. Is there a live example of Passkey wallet? Yeah, there are some Passkey wallets exist in the ecosystem. So one of them is Coinbase Smart Wallet, which is accessible on the browser level. So you can just simply use your browser to access to the smart accounts. Also, there are some mobile wallets, which one of them is we are building called Clave, and like these are 2 different these are 2 different implementations. One is the mobile, one is the web implementation, but they are trying to solve the user experience problems on the ecosystem. Can you show Clave and how it's used in real life? Well, it's probably not allowed to do some the commercial things here, but like you can see on YouTube, for example, you can go to the our website and getclave.io and see the real world usages and how we like simplify the crypto experience for the newcomers and also the existing users. If, for example, iCloud key store safe to use for passkeys, syncing passkeys doesn't have same security, doesn't have some security issue. Probably it's a question. So the iCloud key store actually, this is not the, like normally you have credit card information in your iOS devices, for example. The passkey, private key is stored also at the same place. So when you create a passkey, its private key is stored in the separate place from your device's operating system, so that it's quite safe to put your passkeys. It's called the Secure Enclave. You can search about it on the internet. So I would say it's pretty secure, as like putting your Apple, like your card information to Apple. Yep.
Earlier on, Nicholas Packer from
Ledger.
That's true what you said, but specifically syncing them, there are some pretty serious
During the syncing, the thing is that, for example, for iOS devices, you add your devices to your trusted circle. Of course, there might be some attack vectors, but also some security measures are taken for securely like syncing those passkeys through your devices. Like if you want to access a passkey from your other device, for example, or add that device to your trusted circle, you just have to pass through a two-factor authentication on the Apple side and do some additional stuff. But if you want to not sync it, you can also continue with that option. The example that I showed also like syncs it to your Chrome account so that you can use it in different places. Also, Android, I guess, introduced some new stuff with the passkey. So if you create a passkey on your Chrome, you will be able to access it from your phones also. So they're also bringing some additional things, additional updates. Currently, it supports the ZK Sync Era network. Will it support other networks in the future, such as EVM, Optimism, SUI, Solana? Well, as I previously told, there are some technical difficulties on calculating the same address on ZK Sync and other networks like Optimism and other like EVM chains. For Solana and other blockchains, it's kind of different implementation. So probably our next goal might be going to cross-chain in the future when we have enough technical capability to do it. But right now, we are only going ZK Sync because we're trying to make the UX much more simpler. And when it's cross-chain and the addresses are different and there are no ways to do like multiple, for example, we are currently supporting a social recovery method where you can add your friend as your guardian. So if something happens to your phone, for example, or you lose your passkey somehow, you delete it accidentally, you can request your friend to recover your account in 48-hour time lock. So this is also possible with the account abstraction and with the smart accounts. So when you go cross-chain, you have to like add those guardians in different networks one by one, send transactions for each network. And this is probably going to be solved with the key store rollups in the future if there are going to be a good implementations of them. But yes, since there are some technical difficulties, we are trying to keep the user experience as simple as possible. And yeah, what would be the best method to implement a social recovery in a passkey system? So the contracts that I showed also contains like the contracts are designed in a way that you can add modules to your contract. And one of the modules that we built before is the social recovery. The social recovery contract is simply helps you to recover your accounts using your friends. Their other wallets, you can assign them as the guardian to a smart contract and give some time lock, some threshold, like maybe you will require 2 of your 3 guardians to accept the recovery request, and your account will be recovered after like some time lock time. So in our implementation, we just for simplicity we allow only 3 guardians, and only one of them can complete the recovery process because it's kind of difficult to get approval from multiple guardians, and one guardian is probably enough for recovering your account. We also support ZK email. We will be supporting soon it. The ZK email helps you adding emails as your guardians to your smart contract. So in this case, the email that you send have a DKIM signature, and you can just verify that signature on chain using some cool stuff that ZK email team built. And you just assign your email as a guardian, and then you just recover your account by sending an email. So that's a pretty good feature for the user experience in the real world. What is a typical transaction cost for Passkey transaction on ZK Sync? So typical transaction, as you previously saw, is probably 1 to 3 cents. It depends on the network availability, but it's the same as sending transaction from your AOA. Because there are precompiled contracts, the cost is pretty low, and you don't have to worry about the gas fees on ZK Sync. So yeah, any other questions? I think no questions from the audience, and also no questions from the chat. We can stop a bit earlier. So today we built a simple version of the smart account on our browser. Oh, there's a question. If the Passkey standard is upgraded in the future, how can we guarantee the... I think the question is trimmed somehow. But if the Passkey standard is upgraded in the future, it will definitely be the backward compatible with the existing implementations. But if you want to update your Passkey in the future with the new standard in the future, like let's say if the Passkeys are going to be quantum resistant in the future, you can just simply create a new Passkey and update your owner in the smart contract so that it will continue working with the new standard. Yeah, we built a smart wallet that works with Passkeys today. We sponsored the users' transactions using Gas as paymasters. We sent multiple transactions at the same time. All the codes are open source in the repository that I shown in the beginning. It's in my GitHub account. And you can, of course, use it for your own cases if you have any plans in the future to build cool wallets to simplify the user experience. Thanks for joining.